of proof by mathematical induction here. Here on the left-hand side, we have 3 plus 6 plus 9 plus ... plus 3n. So it's all the multiples of 3. If you add them together, we're being told that that should be 3n times n plus 1 over 2. We're trying to show that that is true. So we'll start out by letting n equal 1. Let's make sure that works first. So in that case, all you're doing is putting in 1 for n. On the left-hand side, 1 for n. On the right-hand side, and just showing that both sides are equal. So if you want, you can pause, make sure that that's true. We can see the left-hand side is just 3. The right-hand side would be 3 times 2 divided by 2, which is in fact 3. So it's true for n equals 1. Then we need to show that it's true for k plus 1. And to do that, we assume that it's true for k. So we assume that 3 plus 6 plus 9, however many we want to add, plus 3k is equal to 3k, k plus 1 over 2. So we assume that that's true, and then we're trying to show that the next term in the sequence is true as well. So now we're going to do the next term, which is the k plus 1 term. So everywhere where we see k, we're now adding a term with the k plus 1. So for us, that will look like, just trying to be thorough here. So next term is going to be 3 plus 6 plus 9 plus the 3k plus the next term, which will be 3 times k plus 1. Notice that I got a little parentheses there. So it's not just 3k plus 1. 3k plus 1 would not necessarily be a multiple of 3 at all. That actually wouldn't be. And so we do need to make sure that we put the k plus 1 in parentheses. And then on the other side, we have 3, and we're going to change that k to k plus 1. And we're going to change that other term to k plus 1 plus 1, or k plus 2 over 2. So this is what we're trying to show. And again, it always comes back to this idea that because we made the assumption that it was true for k, that we already know what this is equal to. And that is the key. So with the fact that that is equal to what you see there, we have 3k, k plus 1 over 2. So I'm using this fact from my first line there that says assume, that that should be true, and then I am going to add to that one more term. And then of course, we need to show that that's equal to this other side. So we just manipulate the left-hand side. We have another fraction, so we want to use that fact to help us. So we need that denominator of 2 so that we can combine our numerators. So I'm going to multiply top and bottom by 2. That will give us 3k, k plus 1, plus 6 times k plus 1 over 2. So notice I did not use the distributive property here, and that's because the right-hand side does not have the distributive property used. So because I don't see it there, I think, well, I already want it in some sort of factored form, so multiplying it out might not help me. And hopefully you can kind of see what's happening here, which is we now have two terms separated by addition where both terms have this k plus 1. And then if you notice that what's left is 3k plus 6, and you notice that that has a factor of 3 in it, then we're basically done. So that's where we're at right now. So we have k plus 1, factor that out, we're left with 3k plus 6 over 2. So we're not quite there, but hopefully you can see that we are almost there. And then we have k plus 1, and we have k plus 2 over 2. And then, like I said, what we want to notice is that 3k plus 6 has a common factor of 3 in it, which we need to factor out. So by factoring out that 3, I'm going to put it all the way on the outside. We have k plus 1, and then factoring out that 3 leaves us with k plus 2. You can probably see why I'm doing it that way, so that I have it look exactly the same as the right-hand side. With properties of multiplication, it doesn't really matter if I have them in a different order, but it's nice to show that the left-hand side is exactly the right-hand side. So check, check, that is true, and that is great. So now we can say this formula, because we have now shown what we need to show, is true for all natural numbers and by mathematical induction. And then we are done with that question. So we'll do one more. It's a little more exciting here. We've got some squareds in it. Got some stuff that's squared. We're trying to show that 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way up to some n squared, is equal to n times n plus 1 times 2n plus 1 plus 6. So let's get started. And I may have to use 2 columns here, thinking about all my space. Okay, so we start, same as usual. We are going to let n equal 1. When n is 1, the left-hand side is just 1 squared, it's just the first term. On the right-hand side, we have 1, putting in 1 for n, times 1 plus 1, which is 2, times 2 times 1 plus 1, which is 3 over 6. And hopefully you see that that is 6 over 6, which is 1. Left-hand side 1 squared, also 1, so here we are. It is true for n equals 1. Now, we assume that it is true for k. So we assume that some arbitrary value k, it is true. So that 1 plus 2 plus however many terms in between plus k squared is equal to k times k plus 1 times 2k plus 1 over 6. Then comes the big part of this, which is that now we show that it's true for the next term. And the next term here is going to be k plus 1 squared. So, so we have our k squared. Next term is k plus 1 squared. I don't want to forget the k squared because I know what the k squared is supposed to be equal to. So I don't want to mess that up. So now we want k plus 1. The next term is k plus 2. And then the next term here is 2 times k plus 1 plus 1. So pay attention to that. The other one's a little easier. I just can add 1 to them. But the third one I need to change the k to k plus 1. So that's actually going to be 2k plus 2 plus another 1 is 2k plus 3. So I'll write that on my next line. Now, this comes back to what we know and love, which is that this piece right here, we assumed that it was equal to this. So we are just going to go ahead and change it and then see if we can manipulate the left side to look like the right side. Always the same process. So we have k times k plus 1 times 2k plus 1 over 6. And then we're going to add to that k plus 1 squared. And we're trying to show that that's equal to the k plus 1 times k plus 2 plus 2k plus 3, and multiply that out, divided by 6. Okay, now as we've done before, we just want that common denominator. Every time here so far you've seen that it's just been a number. So over 6 and times 6, so that we can add these two together. Again, I'm not going to start multiplying things out. That is not necessarily going to help me to multiply things out. Hopefully you can already see that it's not going to help us out here. So if we now combine everything, we have, we're going to have k times k plus 1 times the 2k plus 1. On the other side, adding to that, we're going to have 6 times k plus 1 squared. But notice, common factor, don't forget about it. So hopefully by now you're going to let me do some factoring right away, because when we add these two terms right here, we're going to see that we have a k plus 1 common factor. So that's great, k plus 1 common factor. So I'm actually going to just pull that out. It's just due to spacing. Sorry for anybody that doesn't like it. But I'm going to pull out the k plus 1 from both of these terms. That will leave me with k times 2k plus 1 plus 6 times k plus 1. And like that. And that's all going to be over 6. And on the right hand side, same. So the big thing to see here is on the right hand side, we have that k plus 1. What we really care about is what's left after we factored out that k plus 1. Could it be a trinomial that factors into those two terms, k plus 2 to k plus 3? That's our hope. So we're going to, distribute and add here. Distribute, and then add things together. So that will leave us with k plus 1. And then you'll notice that we're going to have 2k squared plus k. And then we're going to have plus 6k. So we have plus 7k. And then just plus 6 all over 6. Right hand side doesn't change. Now, just as a thought for you, if you think about what this right hand side would be if you multiply out k plus 2 times k plus 3, I mean, that could help you. So what I'm saying is you could help yourself out by just checking, does this multiplied out happen to equal this thing? And if it does, then you know that the factored form of this thing must be this thing. So notice if we multiply this out, we'd have 2k squared, we'd have plus 3k plus 4k, that's 7k, and then we'd have 2 times 3, which is plus 6. So in fact, that is the factored form of what we have over on the left-hand side. So we have k plus 1. That's going to be times 2k plus 3 times k plus 2. And if you're like, well, could we just make it look like the other side? Sure, why not? Let's just make our lives easy and not have to, we know that that's the factored form. So go ahead and make it look like the right-hand side because it is the right-hand side. So we can do k plus 2, 2k plus 3 over 6 equals k plus 1, k plus 2, 2k plus 3 over 6, and check. Woo! It is true for k plus 1. We have shown the two things we need to show, so now we can say that this formula is true for all. And now I'm just gonna throw one more thing at you just so that you've seen it. I'm just going to use set notation. I'm going to say all n, which is an element of the natural numbers, which that's the set of all natural numbers. That's the notation for that. And then by mathematical induction. So you've seen multiple different ways to write it. Any of those ways is fine. But we do say that we have shown it's true by mathematical induction. So don't forget that piece. And that is section 12.5.